Right, our learning targets for today is I can evaluate a limit to infinity, but we're going to amp it up a little bit. But we'll start referring back to what we've already spoken about. We have three cases. One, where the limit is going to be 0, because as we are looking at the end behavior, the denominator grows faster than the numerator. And those y values approach 0 when that happens. This reduces to 3 over x. We have a constant over linear. The linear will overtake the constant. We have two quadratics, one in the numerator, one in the denominator. Here the growth rates are differentiated by the constants. So this limit will always be the ratio of the coefficients because the growth rates are the same. You have the same quadratic functions in the numerator and denominator. And then C is the flip or reciprocal of case A. Here we would have an x over a 3 or 3x over a 1, and we know 3x that approaches positive infinity when x approaches infinity. So we know that this will occur when the denominator grows slower than the numerator. So this is flip-flop. Denominator dominates here, numerator dominates. So here we have linear over exponential. Clearly the denominator grows faster. So here is our 0. We flip it. So now our numerator is growing faster than our denominator. That limit is infinity. All right, well, now we're looking at composite functions. We're still going to use the limits laws and our end behavior to evaluate these limits. So here we pick out the two significant terms, one in the numerator, one in the denominator. Don't pick the first two terms. You have to pick the terms with the highest degree. And here we would simplify that ratio to 8 over negative 2. In the other one, it's 7 over 1. We're using the limit law that says the limit of a sum is the sum of the limits. So this limit is 3. We do the same thing here. We get this end behavior model, this end behavior model. Here, this limit law is the limit of a product is the product of the limits. So I have 8 over 4 times 1 over 10 gives me 1 over 5. Here we're going to evaluate the interior function first, and that result is the argument for this exterior function. So our end behavior model for this 8x squared over x cubed results in a limit equal to 0. The cosine of 0 is 1. We repeat that same concept here. We take our limit to infinity with our end behavior model here. So essentially this limit is the sine of negative 1/2, which is pi over 6, the opposite. And here we can see that I'm taking the limit to positive infinity. However, when I reduce this ratio, it's the opposite of x. So as I send x to infinity, the opposite of x would be going to negative infinity. Here again, when I simplify that ratio, I get the opposite of x. Here, when I send x to negative infinity, the opposite of x will go to positive infinity. We do the opposite. Here, the limit of e to the x is infinity. We can think about the graph. And the limit as x approaches negative infinity of e to the x would be 0, that horizontal asymptote. Or we can take the negative from the infinity, put it on the x, and then have our limit approach positive infinity. And we see we get the same net result. Okay, you could pause the video and read this top portion, or if you already did that in class, you can see that we're dealing with composite functions here within a rational structure, still doing the end behavior. So we have to take the significant term from the numerator and the denominator, but here it's not just a 9x to the 4th, it's the square root of 9x to the 4th. And then we reduce that ratio to get 1 over 4. Again, it's not just an x squared, it's the square root of x squared over 2x. This is the absolute value of x, so now we have to consider that when we are evaluating. This x is always going to be a positive x, while this one is going to assume those negative signs as we approach negative infinity. So I have anything divided by its opposite will be a -1, and then we have that 2 remaining in the denominator. Here we do not have a numerator-denominator structure, but we are going to use the conjugate to make a clever form of 1 to produce an equivalent form for which we will simplify, and then we can create our end behavior model and simplify that to get the value of the limit as 3. We use the same strategy for number 10. We create a clever form of 1 using the conjugate. We get to the point where we're going to take the significant term in the numerator and the 2 significant terms in the denominator, because I have a linear plus this composite function, both contributing to the growth rate. Here, the absolute value is not going to affect anything because we're approaching positive infinity. So I really have 8x over 6x, which reduces to the ratio of 4/3. And here we're just going to set the denominator equal to 0 to get our vertical asymptote. We solve for x because the equation of a vertical asymptote is x equals. Here we take limits to negative and positive infinity to gauge the horizontal asymptote, if there is one. Here I'm taking the limit as x approaches positive infinity of g of x. So we would be left with just an e to the x over the e to the x, which would be 1. Our end behavior model. Well, now I'm going to go ahead and approach negative infinity. So I'm thinking this, if I approach positive infinity, this would be 1 over e to the x, which would approach 0. This is 1 over e to the x, which would also approach 0. So I have 0 plus 8 over 0 subtract 2. That's 8 over -2, which would be -4. So here I have 2 horizontal asymptotes, one at y equals 1, the other at y equals -4.